Hello, everybody, and welcome back to another lecture in Weather and Society. I'm Dr. Zach Hilgendorf, and today we're going to be talking about forecasting in a few different forms. We're going to talk about kind of the process of forecasting. We're going to talk about the tools used in forecasting. Those are going to be two separate videos. And then the last video for this little set is actually going to be on weather folklore. Kind of a fun video touching on, again, the human or societal aspects of weather and how we interpret weather. These next few videos, I'm going to ask you to bear with me. I was leading a field trip this weekend, and my voice is very hoarse, and I'm kind of losing it. So I'm going to try to be as loud as I can. Get the mic up a little bit closer to my face here. But yeah, so a little hoarse, a little raw voice today, but we'll power through. So let's go ahead and jump on into it. First, just want to mention the lecture was mostly inspired by a lecture from Dr. Cliff Mass at the University of Washington titled The Technology and Future of Weather Forecasting, and that pretty much covers what it is we're going to be talking about today. So, weather forecasting, to start off, is a very unique area among science and technology. It breaches a lot of interesting boundaries. Nations, for example, exchange weather data even during cold and warm wars. Uh, we exchange that type of data because we need to know what's going on around the world, and if there's a break in that chain, then everyone suffers from it. Weather prediction covers a huge range of scales from microscopic, like cloud condensation nuclei, to planetary, looking at the entire Earth system and how it moves or how weather changes across that, and how we can forecast that. These are the most powerful computers on the planet. We'll talk a little bit more about these later on, but we're looking at a supercomputer cluster that is used by the National Weather Service here. And it's the only science represented on basically every television newscast. You always look and see, oh, well, what's the weather like today? And that's often being described by meteorologists like we see here. And forecasts are conservatively estimated to save hundreds of thousands of lives and trillions of dollars per year. Why? Well, if you don't know what's going on in the forecast or in the weather, if there's severe weather coming, you aren't going to get out of the way. So this integrated network that we use to forecast the weather is integral to protecting communities, protecting lives, and protecting our infrastructure. Let's look at a few examples here. 2012, Hurricane Sandy, 125 dead, $60 billion, well, over $60 billion in damages, in an area with a population of tens of millions. Only 125, while sad and tragic, only 125 died in this event. Why? Well, it was predicted more than a week ahead of time. Meteorologists and analysts saw this storm developing and coming and were able to warn people much earlier on that this type of an event could happen. We go back to 1938, a hurricane similar in strength to Hurricane Sandy, nearly 1,000 people died. It wasn't in the forecast the day before because they couldn't have seen it coming. 1962, storm in the Columbus Day storm. Also not forecast the day before. Uh, Again, people were, infrastructure and transit was crippled, lives were lost, and there was no warning. January 1993, the Inauguration Day storm. Near perfect forecast. Something's changed, right? Before 1990, the National Weather Service got virtually every major storm wrong, even the day before. After 1990, there was a shift, and they gave good warnings for nearly all forecasted events, and we see that continuing and improving to this day. Now, here we can look at kind of the change over time and how we're getting to, you could call perfect forecasts based off outlook. So That first line, I'll draw it out on the map here. Sorry, this is a bit of a messy graph, but here, this is our 36-hour forecast. This is our 72-hour forecast. The higher you are on the vertical axis, the more error there is. The lower you are, the better the forecast is. Our 36-hour forecast is, for most part, on that line. Let's see right down here. After 1990 into the 2000s, our forecasts were not really that off. Even our 72-hour forecast is really improving over time. Now, if we look back in the 1960s, or 50s, 60s, on through really the 1980s, there was still some pretty significant error there. Most of this improvement comes from things like satellite imagery and satellite data and improving our models that we use. And we'll touch on this a little bit in the next video on how these systems are used to help predict weather. But it suffices to say that we're basically looking on here at the green is kind of our 7-day outlook. The yellow here is our 10-day outlook. The red here is our 5-day outlook, and the blue is our 3-day outlook. And all of these, sorry, I meant to erase that there. All of these are starting to improve, and we're noticing that that range that we see, for example, over here, that range of potential anomaly correlation, where, in this example, we're looking at kind of ranges in basically predictive capabilities, is almost a flat line by the time we get over towards the 2000s. Here we can look at official annual average track errors for hurricanes and tropical storms in the Atlantic Basin. And again, forecast error is decreasing substantially. And all avenues, the 24-hour, the 48-hour, the 72-hour, the 96-hour, and the 120-hour forecasts. So we're improving. We're improving our models. We're improving our predictive and forecasting capabilities. Weatherman jokes or meteorology jokes aren't really appropriate any longer, because as a science we've moved so far past that we understand the Earth better than we have in human history. And it's only improving with technological capabilities, improving satellite sensors, improving formulas and models. We're improving our ability to accurately predict the weather. The key technology of modern weather forecasting is what we call numerical weather prediction. Now, the first successful prediction of weather was made in April 1950 using the ENIAC computer at Maryland's Aberdeen Proving Ground. Way back when, they were you're basically looking at what it is right now. Think of this as a very rudimentary computer. The basic idea is, if you can determine the current state of the atmosphere, you can predict the future using equations that describe the physics of the atmosphere. Now, we're not going to really dive into that, so don't worry about that too much. But these equations can be solved on a 3-dimensional grid. We're looking at basically surface position and atmosphere, right? All these different aspects form this 3-dimensional grid. And if we understand how to predict the movement of weather through numerical prediction, we can understand how a system might move throughout 3-dimensional space. Observation collection is needed to create the initialization, basically the starting point of these predictive measures. So there's a whole slew of different technologies that we will be talking about much more in the next video, but that we use on the surface, in the atmosphere, or even in space to help predict and forecast weather. So kind of the baseline here, one of the equations used to predict the weather is Newton's second law. Force equals mass times acceleration, F equals ma. Mass is the amount of matter. Acceleration is how velocity changes with time. Force is just a push or pull on some object, gravitational forces, pressure forces, or frictional forces. This equation serves as kind of a time machine for us. Why? Well, If we look at it, the initialization gives the distribution of mass, or how much air there is and where that air is, and allows us to calculate various forces. Then we can solve for the acceleration using force equals mass times acceleration. With the acceleration, we can calculate velocities in the future. Similar ideas are here with temperature and humidity, but they use some different equations. Now, the basic equations, and I say basic, these are what the basic equations are. We see the wind forecast equations, continuity equations, temperature forecast, moisture forecast, and hydrostatic equations. We are not going to be doing any of this in this class. That is for much deeper meteorology classes. Um, but this is just kind of showing you what the numerical side of things, some of the primitive ways that we just interpret weather, and we interpret that force and how that force drives weather across our surface. Now, numerical weather prediction is limited by the available computer resources. We'll talk about the supercomputing systems that NOAA uses briefly in the next video. But as computer speed increases, the number of grid points that we use can increase. We can, for example, maybe we had a few grids in the past. But then the more our computer models improve, the more we can subset these grids and improve our ability to break down local changes and deviations within that model. And as technology improves, this potential is only going to get better. But just as important as this computer revolution has been, the weather data revolution with satellite imagery, for example, or satellite sensors, allow us to basically look at the three-dimensional data over the entire planet, sometimes multiple times a day, depending on the satellite that's being used. This is an example from one of those satellites. We're looking at moisture content here, or cloud distribution. So we're able to track moisture across the planet. We're able to look at cloud movement and use that to track winds. We've seen these flags before when we looked at weather station models and tried to understand, how strong this indicates the flags may be, usually in knots. So this is a little bit higher up in the atmosphere, a little bit off the surface, but this is kind of showing how we can use clouds to track wind. Our satellite constellation, one example, the NOAA Polar Orbiter. And we'll talk more about the satellites, briefly in our next video here. But satellites have really revolutionized these trends and our ability to see these trends play out in real time. Satellite sensors provide thousands of high-quality vertical soundings daily. So we've talked about soundings before. We're not really going to dive into them too much, but it's basically a way for us to pick apart the atmosphere through vertical slices, and look at temperature, dew point, and through that humidity. So we're basically able to see through multiple layers of the atmosphere, well, through the lower layer of our atmosphere where weather really occurs within our troposphere, at different pressure levels, how these factors, temperature and dew point, for example, some of the prominent ones, are changing over time. And as far as impacts go, the addition of massive amounts of new observations is allowing us to improve our weather prediction capabilities. We're now starting to see frequent examples of forecast skill past 1 week. Hurricane Sandy is just one example, and that was from 2012. Where we are now is just continuing to improve. Here, we're looking at observed versus forecast systems for this area off the West Coast. And they match up. This is 7.5 days in the future, and they match up pretty well with what ended up happening. And this is only going to improve. Increasing resolution and better models aren't going to be enough, though. The next major revolution in numerical weather prediction is going to come from somewhere else. But where is that going to be? Well, the way we've been forecasting, you could call it flawed. The atmosphere is inherently chaotic, and small uncertainties in how we start to forecast weather have very major impacts on the forecasts themselves. We think of, unlike, like a pinball game, very slight deviations can send that ball flying wildly in ways that we didn't previously predict. Similarly, there are uncertainties in processes like how clouds develop, how precipitation forms, and that produces further uncertainty within our forecasts. So all forecasts have a lot of uncertainty baked into it. Now we're getting better, substantially better than we used to be, but that uncertainty generally increases in time. So a 36-day forecast, and we saw that on those graphs before, is going to be much more accurate and much more realistic than a 180 hour for, something way out in the future, a week and a half, the 10-day, for example, versus the forecast that's for tomorrow. Um, we can look here at the 10-day, for example. It's hard to say that what we see down here is actually a realistic representation of what could be happening, just because we're not really there yet. We're getting there, but we're not there yet. So weather forecasters need to tell users about uncertainties within that forecast and give forecasts in terms of these probabilities. There's an approach to handling this issue that's being developed by the forecasting community, and we call that ensemble forecasts. Now, ensemble forecasts are basically, instead of just making a single forecast, you make a bunch of different forecasts with slightly different initializations or different models that model and use physics to kind of predict the weather here. It's possible to do this now, whereas it wasn't previously, because we have the processing capability and the computational resources. So, for example, this tropical storm that we're seeing here, we see all these different tracks of where it could play out, and maybe the probability is baked into how that storm could move, maybe towards the south or towards the north. It could curl like we see happening here. Maybe this white line then is the real track, and that is used to update that storm track regularly. So the ensemble can give probabilities, and the ensemble mean is more accurate than any individual member. So you have all these variations in prediction, but that average, the mean, is what's going to be most likely to be relatively accurate versus just having a single forecast or single prediction. In the future, it's estimated that these ensembles are going to dominate the forecasting world. So the meteorological profession is rapidly gaining the ability to produce these high-resolution probabilistic weather forecasts and analyses. Probabilistic forecast analyses will be available for a wide range of weather parameters. We also have what we call the nowcasting revolution starting. Nowcasting, as far as the American Meteorological Society is concerned, is a description of current weather and a short-term forecast varying from minutes to a few hours, typically shorter than most operational short-range forecasts. This is very local based, and it's used to say how might the system change in a much more fine-tuned fashion. During the past decade or so, our geographical and temporal specificity of the information that we use has increased greatly. We have a lot more sensors out in the world. We're always adding more sensors to the atmosphere or more satellites. So we're densifying our data set. The traditional approach of weather information dissemination is kind of incapable of delivering what we need and how we can now provide it. Typically, TV weathercasters have about 2.5 minutes to convey their forecast. But some places, like smartphones, for example, are really an ideal solution for disseminating this data. They have a lot of bandwidth. They know where they are, so forecast information can be tailored to the specific user, and there's a pretty substantial computational capacity there. So, for example, one way that this is already being put into practice is when I was living down in Phoenix for my PhD. If you were within the geographic region of a haboob warning or a monsoon warning, your phone would go off saying that a haboob was on its way and that you needed to take shelter. So we're seeing this starting to pick up and these trends starting to improve, and we're seeing this really start to come into its own. So, smartphones offer a powerful portable platform for viewing weather information, forecasts, and warnings. Now, obviously, these phones look like they're somewhat out of the, I think, the early 2000s, but that's okay. Lots of good examples of current conditions, radar, and forecasting on these phones. So we'll ignore the fact that one of these definitely looks like a BlackBerry and maybe a Razor and maybe things that y'all don't understand or weren't aware of from a bygone era. Um, and there are now thousands of weather apps for smartphones, and there are some that aren't even out yet, right? There are some that are going to come out. I have, I think, three or so weather apps on my phone alone. One called is it Windy or WinTY. I've got another one. I use Weather Underground. Um, I've got some others for looking at different aspects of the weather. So each one is slightly different and has different graphical user interfaces to kind of allow you to pan through different aspects of the weather. So these are only going to improve with time. And we've got the weather adaptive society. So advances in computation, control, and communication allow society to react quickly and effectively to weather information. At the same time, these forecasts are going to rapidly improve. And together they allow effective real-time weather adaptation for us, the user, the end user, and the person who that data is trying to be disseminated towards, or that information or that forecast. So in this video, we just talked about kind of how forecasting has changed and where it's going in the future and what those trajectories are. So we're going to dive into some of the tools used for forecasting in the next video, and then we'll have a fun one, and we'll talk about weather folklore or weather adages, for example. So we will see you in the next video, and I hope you have a great day. Thank you.